So the topic today is tips and tricks for modeling plasticity. Just for those not familiar with us, the CAE Associates, we're one of the first ANSYS channel partners located in Middlebury, Connecticut, specialize in FEA, CFD, and electromagnetic simulations. And if you visit our website, you'll notice an extensive resource library, including material from case studies, blogs, and classes, schedules, and, of course, information about future webinars. And details on our particular webinars, today's tips and tricks for plasticity, previous webinars, or also you can get some detailed information on the website. And, of course, if you want to view this webinar in the future and all of our previous webinars, they are easily accessible on our YouTube channel. So today's topic is tips and tricks for modeling plasticity. The items I'm going to cover are identifying analysis where simulation of plasticity might be important to you, do's and don'ts in terms of setting up your material properties, insight into obtaining convergence, and more information about how to evaluate your results from running a plastic analysis. So when should I model plasticity? Modeling plasticity, again, should be something you do after initially you run a linear elastic checkout model to make sure that you've prescribed the correct boundary conditions, loads, and the functionality of your simulation makes sense. Adding plasticity is going to add computational complexity, but it's also going to add solution accuracy. So it's going to give us a better representation of the final stress state in our structure where there may be local or extensive plasticity. It's going to give us the ability to quantify permanent sets. So we take our coat hanger and bend it back and forth and let go. Where's the final position that it's located? That is something we can predict analytically. So better predictions of displacements, and then from a design investigation, from a failure evaluation, we can look at the total amount of accumulated plastic strain and compare that with design criterion to evaluate our particular product. So as part of putting together a little webinar, I always like to do a little history search. So as many of you probably know, one of the three of the most important four founders in the area of plasticity are Tresca, who did his work in the early to mid-1800s. He was really the one that invented the first yield surface, the shear-induced permanent set. And then Bausinger came along a little later. His claim to fame was how the yield surface actually moves during a cyclic-type loading event. And then, of course, the most famous is Richard von Mises, whom the yield criterion used predominantly in basically all finite element codes are based on this cylindrical yield surface that we'll spend a little more time on in this webinar. So applications of plasticity models, primarily in the metals, but we also see applications in other materials such as soils or concrete reinforcement, even bone and certain plastics. In terms of analytical simulations of plasticity, some examples, common uses are overspin of discs, balloon expansion of stainless steel stents, metal forming operations, surgical staples is an example I'll show in a second, detailed modeling of threaded connections, to name just a few. So there's an example of a surgical staple. You notice that in this particular example, we see the item on the right deforms basically correctly. The item on the left is one that buckles. It's something that we can predict with a plasticity model, setting up an imperfection of the model to demonstrate this plastically induced buckling phenomenon. Another application would be an elastomeric bearing. So this is an elastomeric bearing with a lead plug. This particular example is used in a bridge support to be able to withstand or absorb energy during an earthquake event. And analytically, you can take and model the plug layered composite material explicitly. But you can also often create simplified models. In this case, a single element model is created with a nonlinear plastic stress strain response, and both models accurately predict the hysteresis energy absorbing behavior that occurs with this kind of elastomeric bearing. Another example is a medical stent device. So this is a stainless steel stent shown undergoing expansion. Just an interesting little side note on this example. The reason it says test case to satisfy Peter is this actually was run as a 2D simulation, but we used some graphical manipulation to map the data from a 2D onto shells and then do an expansion. So it gave the appearance where we modeled the entire stent, where in reality the model was just the smallest repeatable segment. So on to some definitions. So when you look at plasticity, you do research, whether it be in your textbook or Wikipedia or whatnot, you will see certain terms. So first, the proportional limit. The proportional limit is where we change from a linear variation, a linear response in terms of stress versus strain, or this can also be force versus displacement. We have an elastic limit where we get to the point where now we see some permanent set. We take our loads off and our structure does not return to its original position. The slope of our linear region is our Young's modulus, of course. The yield stress is typically explicitly defined as the stress required to create a 0.2% plastic strain. We have some hardening representation in terms of when we go beyond the yield surface. We have some ultimate stress, and typically for metals, particularly when we get to the point of failure, we see some necking of behavior. So that was the theoretical definitions. From an analytical perspective, we basically simplify things to do selecting a certain single yield point, which is the point where plasticity begins. It's also the point after the linear behavior ends. So we kind of join those points together. We have a loading curve that occurs in the linear regime as well as in the hardening regime. Unloading always occurs back down the original stress strain curve. The amount of strain induced is a combination of elastic strain, where it's a recoverable deformation, and the plastic deformation, which is the permanent deformation. Now, a question I had last time was, what if I have a condition where the hardening slope, I want to make it greater than the initial slope, and since that's not valid in standard plasticity theory, what you can do is kind of trick your analysis whereby you put a very, very small slope at the beginning, and then you could have a circumstance where you could then add a slope in the hardening regime that might be greater than the elastic modulus. A non-standard practice, and really not too many materials actually behave like that, but there's always kind of those tricks of the trade that sometimes can be applicable. So one of the things we got to be careful about when we're creating our analytical model to predict the actual behavior is to make sure we account for the correct stress and strain relationship. So from a small strain perspective, taking a small deflection or looking at the a linear relationship can be used. But once we get into significant amounts of strain where we're actually changing and updating our mesh. We're truly doing what is applicable to, from a theoretical perspective of true stress and log strain. And so to characterize that, if we look at a simple tensile test behavior and we plot stress versus strain or force versus displacement, which is the engineering values, you see that our curves look something like this, where we see an initial linear curve, we see some hardening curve, and then ultimately down to the necking and failure. But from an analytical perspective, what we really want to look at in the finite element model is what we're actually characterizing is the change in shape of these elements in where the plasticity occurs. So we're really looking at a true stress versus log strain. Now, luckily, it's a straightforward calculation to convert our input data. So when we're inputting data into ANSYS, we're going to input log strain information and true stress. And if we take our physical test, we simply use the simple equations of the log 1 plus the engineering strain and the stress is 1 plus the engineering strain to convert to data that we can use directly applicable to our large displacement finite element calculation. So one of the things that you'll notice is the difference in the curve shapes we just talked about. The other thing is, from an input perspective, is that ANSYS will keep the points beyond a multilinear curve to have a zero stiffness. So we want to make sure that we extend our curve well beyond any points that we may see in our analysis. The conversion from the test data into input to ANSYS is simply done by using a spreadsheet. So I have the engineering stress strain, and I simply plug in an equation to convert to the engineering or the true stress. I convert to the log strain, and then the input asks for the plastic strain versus the true stress. So here's our true stress. Our plastic strain is simply equal to this total strain minus the elastic strain, where the elastic strain is the total stress particular entity divided by Young's modulus. And you can just simply plug that into a simple equation in your spreadsheet. Now, what we've talked about here is a uniaxial test condition where we're just looking at the stress components in a single direction. In reality, we have a three-dimensional stress state. So to go from the single uniaxial stress state to the three-dimensional stress state, we're going to develop some kind of yield criterion. So in this case, we're looking at a yield criterion where we differentiate the hydrostatic stress state, which does not induce plasticity, to the deviatoric stress state, which is what that does induce plasticity. And a general stress state can be divided into these two components. So we divide those, or we perform that operation to compute the stress quantity that we can compare back with our test data, and that's where we use the von Mises yield criterion, which is defined as such, the equation below, which is written in terms of components. You can also use principal directions, which is simply the square of the sum of the differences of the principal component stresses. And this was developed and finalized by our friend von Mises we just talked about a couple of minutes ago. So the three-dimensional stress state, if we look at that in a uniaxial condition, we notice we saw this bilinear curve. If we look in the three-dimensional stress state, we look at a circular surface looking down the axis or a cylindrical surface. Now, when we take this yield surface and transpose it, move it, we offset from the yield surface. We offset in a direction typically normal to the surface for metals, and that's what's considered or documented as an associative flow rule. So we're going to take this surface and extend from that in a perpendicular direction. And we're going to look at two different hardening rules. Either we're going to translate the surface, which is kinematic hardening, which is applicable to small strain type problems and cyclic loading, or we're going to actually enlarge the yield surface, which is the isotropic hardening law, which is more applicable to very large strain type problems and cyclic loads of maybe a cycle or two, but not large number of cycles. So again, the kinematic surface is a translation of the yield surface, so when we unload our structure and continue to load in the other direction, such as going from tension to compression, we will yield again at 2 times the yield surface. And this behavior is also known as the Bouchinger effect from our friend from earlier as well. If we look at the isotropic behavior, this says that I'm in a condition where that in order to yield in the opposite direction, since I'm growing the yield surface, it's 2 times sigma prime, or the current stress state. Now, if you notice that if we don't do any unloading and reloading, if we don't go back into the plastic regime, both these curves are going to look identical. There are also a number of advanced plasticity material laws that we're not going to talk about in detail, but just be aware these are available in ANSYS to deal with anisotropic behavior. So if you have different yielding in different directions, cyclic loading can be looked at in terms of a ratcheted shakedown response with the Chebosh model. The Anand material law is often used for rate-dependent plasticity. In particular, it's used for evaluating cyclic loading on circuit board solder balls. And then the Gerson model is one that takes into account ductile porous metals subjected to damage. Most of the time, however, people are dealing with either a kinematic or isotropic hardening law. And for these 2 laws, there are 2 ways of inputting the material data. The simplest way is to use a bilinear stress strain curve. So we're just looking at a single 2 inputs for the plasticity, which is a yield stress and a slope for the tangent modulus. Or the multilinear curve, where we're putting in, again, the Young's modulus, and then we're putting in a series of points, and these series of points represent the true stress and the plastic strain increment. So to define this data, it's relatively straightforward to do it in the workbench setup, but it's always a good idea to spend some time testing any material inputs you use on a simple model rather than jumping directly into your more complex model. And what I have shown here is just what I've created is, in this case, there's 5 different single element models I'm using to evaluate the response. So if we look at this, if we come up to my ANSYS workbench session and I go into the engineering data, if I wanted to add a new plasticity material law, I can go and simply right here just click and say I'm going to put in idealium or whatever material law you're going to use, and I can drag and drop the bilinear isotropic hardening onto that, and it's going to prompt me to put in a modulus of elasticity. It's going to prompt me for a Poisson's ratio, and then a yield stress. Maybe this is mild steel, so 36,000 KSI or PSI. And then you're going to put in some kind of slope for the bilinear hardening. You do not want to put a 0 slope in, because a 0 slope will give you computational convergence issues. So you notice I put in a value, in this case of 1e⁵, which is a fairly large number, but relative to 30e⁶, it's a fairly small number. So this gives me, in a sense, the effect of a linear hard, or a very little hardening. So it's essentially an example of elastic, perfectly plastic response. If we look at some of the multilinear curves, you notice that the input data starts with 0 plastic strain because the first data point is the yield stress, And then the corresponding points in addition to here are the points that include the plastic strain and the stress, as I indicated earlier in the presentation. So, recapping, we can just, in engineering data, we're inputting the material properties. We choose from one of the material laws available in ANSYS, specify the particular hardening information, whether it be a bilinear type curve or a multilinear type curve, and make sure, again, that you put in some positive tangent modulus. You can make the multilinear curves temperature dependent, where ANSYS will do interpolation between the values. It uses the Rice's method in terms of hardening, so you change temperatures, you will not see a induced plasticity by just a uniform temperature change. And we can also look at putting in these multilinear curves, the isotropic and kinematic hardening. And as I mentioned, make sure that the curves go well beyond any plastic strains you might see. And you can take this information and just Control-C, Control-V from a spreadsheet and dump it right into your particular ANSYS input. So here's an example showing a spring with permanent set and plasticity. And you notice that I'm ramping the load on very slowly because in this case I'm inducing fairly significant amounts of plastic strain, and from a computational efficiency I find that using the more plasticity, the more material deformations that you anticipate, the more intermediate sub-step solutions you should account for in your analysis. Because it's inefficient when ANSYS does bisections. You see in red, there's a couple places where it did some bisections, but by and large, I just ran lots of intermediate solutions. You also see the notice here as why starting with a simplified model makes sense, because I'm running 1,400 iterations. Well, I can do that with a simple finite element model much easier than I can do with a complex finite element model. So let's look at that particular example in a little more detail, and we can then cover some of the input quantities. First thing I want to show is the finite element mesh. 2D model, I used inflation layers to force the nice uniform mesh close to the surface because that's where we're evaluating the plastic strains. I also used a displacement control solution. I ran this in 3 load steps, where in the second load step, I just did a very, very small amount of unloading. And that typically gives me the best convergence because ANSYS has to convert from being on the loading curve to the unloading curve. And computationally, by doing that in a very slow process, is much more efficient to get that problem to solve. Post-processing, I can look at things like plastic strain and an equivalent plastic strain. We'll talk about those in the post-processing. So, just to clarify, we're looking at displacements. They're based on the original coordinates. Stresses and strains we're looking at based on the updated deformed geometry. Our stresses and strains are computed at the integration points. In a linear analysis, these are extrapolated to our nodes. In a plasticity analysis, these are going to be copied to our nodes. Well, an anomaly that sometimes occurs with a coarse mesh is you may be at that time in the loading sequence where the copying has not occurred because we're below the yield surface, but the extrapolation produces stresses beyond the yield surface. So it is possible to plot your models and say, wait a second, why is ANSYS predicting stresses beyond the yield? Well, often the reason for this is simply your mesh is too coarse, and that extrapolation versus the copying is occurring where we're just on the cusp of yielding. So in the post-processing, there are a number of different feature functionalities that we want to look at in terms of being able to understand our response. We can look at the hydrostatic pressure state. Sometimes this can be helpful for numerical convergence, and this is showing, as we talked about, where we divided our state between the shear and the hydrostatic pressure. The stress ratio shows where we are on the stress-strain curve. If the stress ratio is 1, that means that we're actually on the yield surface. If we've done some unloading, the stress ratio will be less than 1. One of the other things you'll notice here is these two entities are user-defined quantities because not all the post-processing and plasticity is available directly in the pull-down in the GUI, and we'll show an example of that in a second. Look, we can look at the elastic strains just directly from the pull-down. If we want to look at component plastic strains, we need to use the user-defined functionality for that as well. Total strains, so we can look at the total strain, which is the elastic plus the plastic, and we can get that direct from the user-defined functionality. In terms of a single quantity of how much plastic strain is induced in our model, the von Mises plastic strain quantity, or the pull-down for the equivalent plastic strain available in the GUI, just to understand, this is the amount of strain that would induce permanent set in our solution. If we have a cyclic loading behavior, this is not the total amount of accumulated strain that is typically used in a design perspective. So from a design perspective, we need to insert in the user quantities this NLEPEQ, which is the equivalent plastic strain, which is the summation of each time we've had yielding occur. And this is typically used to compare with a design limit. Now, if you look at this response, if we're just in the monotonic condition where we haven't done any unloading and the corresponding yielding in another direction or under cyclic loading, unloading, and re-yielding, these two quantities will be identical. But they are different when we have the incremental response where we have the effect of the nonlinear, the incremental plasticity. So let me just show that real quick. So on this particular simple example, I have that I've created now. This is the model that has the several different tests where I have a series of different models that I've run all at the same time. And if I look at the equivalent total plastic strain, you can see it goes up and down because this is a loading-unloading cycle. But if you look at the NLEPEQ, this is always increasing. These user-defined quantities are simply accessed by highlighting solution under a worksheet, and I can scroll down here and choose, for instance, this NLEPEQ, directly right-click and say create a user-defined result. And that shows up in the GUI, and now I can process that for the entire body, or I can select a particular body that I want to evaluate that result for. And you notice that you see this always positive increasing value for that particular quantity. So what if my model doesn't run and converge? What are some of the things I need to look at? Well, you may have too large of increment of plasticity. You can use the cutback controls in ANSYS sometimes to limit that. The default is 15%, which is quite a large number, so I would recommend using a smaller number than the 15% value. Force unbalance is typically the #1 reason things don't converge, so controlling the forces, and typically the solution process there is applying more intermediate steps. You may get error messages or warnings about problems with the element shapes. These may or may not be element shape related. If your unbalanced force is a very large number, it may be simply just a system of you're applying a load too fast, or you have some singular condition, or you have some instability, etc. But if the unbalanced forces are not large, then this may be something real, and you need to adjust your model accordingly. So element distortion can be overcome by adding intermediate substeps, adjusting the mesh. So start with the mesh shape where under deformation it becomes more square. Other advanced features such as rezoning, you can change element type formulations. Sometimes going to a more simplified model is a way of getting rapid convergence and understanding behavior. So go to shells and beam elements, which will converge and run much faster than the very large tetrahedron mesh model. So some general rules of thumb, just to conclude, is simplify your geometry. You want to get the most bang for your buck in a plasticity model of each element. So I recommend trying to sweep mesh as much as possible. Use lower order elements since the number of integration points that you're going to evaluate your plastic stresses and strains are the same. The more plastic strain, the more deformations, the more intermediate substeps I would recommend. Displacement-based loading are always better than force-based for convergence. They eliminate rigid body motion. They give you a much more stable response when you go into the plastic regime. And then for some cases where we're dealing with very large strain, we have strain rate issues, etc., sometimes changing to an explicit methodology can be a more efficient process.